Good morning. My name is Ken Cantrell. I'm from NetApp. I help run part of the performance engineering, performance analysis team.
And I'm Nick Principe from IX Systems, the makers of FreeNAS, and I'm in charge of the performance engineering team.
So we're going to talk kind of jointly today about the new AI, ML, and genomics workloads that are going to be part of the new SPEC Storage benchmark. We're going to kind of tag team this. Nick's going to start off by talking a little bit about the SPEC SFS committee and SPEC itself. Then I'll talk about the AI, ML workload. Nick will go back and talk about the genomics workload. And if we have time, we can talk a little bit about just other miscellaneous things happening in the next version of the benchmark.
All right, so we already did a poll before we started, but how many of you have heard of SPEC or a SPEC benchmark? So almost everyone in the room, so that's really good to hear. So if you're not aware, SPEC is a nonprofit industry standards organization that was actually founded back in 1988. So at the beginning of, the beginning of this year, we did the 30th celebration at our annual meeting. So that was a lot of fun. But the point of SPEC was to come together and make fair industry standard benchmarks that were actually useful both to the companies and to the end users. So it's quite an exciting organization. It's all of the competitors get together and try to agree on what a benchmark should look like. SPEC has several different groups within it, sort of major committees, and that's split between the open systems group. There's also a graphics group, an HPC group, and a research group. We're going to mostly focus on the open systems group, which makes the benchmarks most relevant for most of the audience here. That's where we have the CPU benchmark, which is the most well-known benchmark, I believe, that SPEC produces, at least from the open systems group. And also the storage subcommittee, which used to be SFS, until we realized no one knew what SFS stood for. In fact, we barely did. So we made it storage because we'd rather be named after what we're trying to test. There are also many other groups, Java groups, Power groups within Open Systems Group, but we're from the storage group, so that's what we're focusing on today. So a little disclaimer, everything we're going to talk about today is basically pre-release and is subject to change. We intend for these workloads to be in the next release of the benchmark. Tentatively, we're calling that Storage 2020. But again, everything is still up for change potentially before the final release. The benchmark or the workloads may look different. The scope of the benchmark may change. Which workloads are included at release may even change. So it's sort of a warning, but it's also encouragement. If you aren't involved right now and you're interested in these workloads, there's still time for you to get involved and help us make the workloads better and more realistic. So maybe if you want to participate, you do need to be a SPEC member. You may already be one. This is the list of the SPEC OSG member consortia. So that includes our sustaining and associate members. Sustaining members get the most access, but if you see your company name on here and you weren't aware of it, you can get the latest versions of the benchmark, and you can participate if you're a sustaining member in the activities, our bi-weekly meetings with SPEC Storage. And that's at no cost. There's other benefits too, like free publication and stuff like that. So what is the SPEC Storage benchmark? The current active version of the benchmark is SPEC SFS 2014, and we've extended it a couple times since we originally released it back in 2014. So what is it? It's the industry standard storage benchmark, especially for file access solutions, building on the heritage of SFS 97 and SFS 2008. And it's used primarily at the visible level. If you go to the SPEC website, what you see mostly are marketing and competitive positioning results to compare, this is what my solution can do, this is the large number I can get with my solution, and then other vendors publish and see if they can, beat those numbers. But also, it flies under the radar, but I think most people actually use the benchmark for internal testing, for sizing and stress testing and validating their solutions, because it presents very complex workloads that can scale very high. And I think the key thing and this is hard to get from any other benchmark, is it can have a very high metadata component to the workload. So with a lot of other tools, you really can only test reads and writes. But now you can test the various POSIX metadata operations, making directories, deleting files, changing the permissions on a directory, things like that.
Can I add one?
Sure.
Major use case, regression testing.
And
Plugged into it. A lot of people plug into the framework to make sure they're not regressing them.
exactly, and BP just pointed out that it's also used for regression testing, and it's a very good way to quickly get a feel for how has your performance changed between internal builds between major releases. Right now in SPEC SFS 2014, we have 5 major workloads: database, software build, VDA, VDI, and the newest one is EDA that we talked about at a previous SDC. Right now with Storage 2020, we're proposing adding genomics and AI image recognition. Those are proposed, and we're going to talk about those here today. The key thing about SPEC SFS 2014 and 2020 is that it measures at the application level. It's not synthetically generating workload, it's actually generating I/O the same way an application would and at the same level. This lets you test a broad range of products, and you can test things that you wouldn't normally be able to test. I think the clearest example is you can see published results with IBM Spectrum scale storage, which typically that wouldn't have been able to be tested with previous versions of the SPEC SFS benchmark. Question?
Yeah, so if I look on the number of results published in SPEC SFS 2008, the number of results in 2014, there is a big difference.
Yeah, so the question is, there's a big difference between the number of results published with 2008 versus 2014. The storage landscape changed a lot between 2008 and 2014. There were a lot of acquisitions. A lot of the smaller companies got absorbed. Some companies went away. And also the transition from the benchmark generating the load versus doing application level testing has been a difficult transition. So we're trying to find ways to make that easier and increase the volume of results.
So we expect the storage 2020 that will go.
I think having these sorts of workloads will increase the interest and also bring in hopefully some new storage players. But it's important to note this is not just a NAS benchmark. You can test block storage with it as well. You do need a file system on top, but there's a very easy way to do that, and that's in the backup slide, so we may get to show you an example of that, depending on how we go. For additional information, we've done a lot of presentations here at SDC, so those are on this slide. You can refer back to them if you didn't make it to those sessions. There's a lot of info in here. And with that, I'm going to hand it over to Ken to talk about the AI image processing workload.
So interesting, slides aren't updated entirely. So all of the workloads that we do generally have a workload sponsor. NetApp is the workload sponsor for the AI ML workload. Dell EMC is the workload sponsor. It'll be on the slide for the genomics workload. So we've done a lot of the work in that, and I'm going to point out Sung Han sitting up here in front because he's done a massive amount of work to actually gather a lot of the data. The other person who's not here, his name is Don Capps, did a lot of the underlying analysis that you'll see here. So I'm mostly representing the kind of work that they've done. And many of you, I hope that many of you will know a lot more about AI and machine learning work than I will. I'm more of a storage person than I am an AI person. So you are welcome to ask as many questions along that line as you can. I will answer as many as I can. But a lot of, you'll see where the direction of this is going. So AI ML, if you're going to make an AI ML benchmark, that's a little bit like saying you want to create a virtualization benchmark. Because a virtualization benchmark doesn't mean much in and of itself. It depends entirely on what you're going to virtualize. Just try to virtualize a database, the I/O patterns for a database, that doesn't even make sense, because if you're going to do a database, you've got to decide what the database is running. Is it an OLTP workload or a DSS kind of workload? All those look different than a home directory workload. So we knew we wanted to have something that helped cover at the AI ML market, but that topic's too broad. So the first thing we had to do is decide, what do we mean by AI ML and what is this going to try to represent? So let me go all the way back for just a minute. Those workloads that you saw before, the EDA and the software build and so forth, the goal of the SPEC Storage, used to be SFS benchmark, is to take real world workloads and then reproduce them much easier with a lot less overhead. So we want them to be as real world applicable as possible. And so what are we trying to represent here? We realize that to answer this, we've got to go through a few questions. We have to pick a focus area and then pick a framework that we're going to try to both trace and then reproduce that trace of. So an AI/ML framework. Within this world, there's various models that you could be using, and so we need to pick a model and then pick a data set. So for a focus area, AI/ML covers a huge amount of topics. So there's a McKinsey report out there that lists what's considered AI/ML. It goes everything from like just a basic Markov model up to things like neural nets and deep learning. That's where we decided to focus. And then within that, the McKinsey report pointed out from their view that image classification was, I think the phrase was, the most essential of all business uses for neural nets. So we decided to look at image recognition, which is kind of a superset of image classification, as what we're going to try to do. Within that, you need a framework. So there's a lot of different frameworks. You could try to represent the workload of Caffe or Caffe2 or Torch or PyTorch or a number of others. We decided to implement or to trace and then to re-implement something based on TensorFlow, largely because I think it's the most widely deployed AI/ML framework still out there. So we use TensorFlow. There's another value of TensorFlow, namely that as part of NetApp partnerships looking at AI/ML workloads, I have access to an excellent TensorFlow-based POC environment that I could get some excellent traces off of. So that was useful as well. Within that, you need a model. So what are you going to implement within TensorFlow? The quote from Lambda Labs pointed out that fewer than 5% of our customers are using custom models. Most use something like ResNet, VGG, Inception, SSD, or YOLO. And again, we want this to be as broadly applicable as possible. So custom models were off entirely, but what did we want to use after that? What we actually did is we got traces based on, we got 3 traces, one from ResNet, one from VGG, one from SSD. We also got one from, well, we're hoping to get one from Inception to see how it fits into that as well. Now many of you may know that there's a lot of differences internally between like VGG and SSD and the kind of information that's passing back and forth between GPUs and CPUs. Interestingly, what we found through the traces is that the kind of I/O that's being issued from each one of those models to storage, your file-oriented I/O, is very, very similar between all 3 models. There's some differences in intensity, and so part of what we did is we took our traces and we aggregated them together to have kind of a composite model of intensity. But the I/O patterns, whether it's random or sequential, the basic I/O sizes, they're very, very similar between the 3 models. So like we could we could feel good about ourselves by taking 3 traces and putting them together. You need a data set, so kind of going with the model work. We used 3 different data sets because we didn't want to limit it to just a single data set. So we used the Cityscape, the ImageNet, and the Cocoa data sets. There is a mapping because there were 3 runs, 3 data sets, 3 models, that it all goes together. I don't remember exactly what the mapping is at the moment. So if you're into AI/ML, you'll recognize that this is just a high-level overview of one part of what was happening in this. So once we have our data set, yes, sir?
So for the AI/ML workloads, especially for the deep learning networks, so you will have multiple simultaneous computations at each layer coming out the enormous number.
Yes.
And you will be utilizing that for the next layer. So which you need not to be stored permanently in your storage, but need to be cached.
Hold that thought, and I'll come back to it. There was a question about the pipeline and the workflow and which parts of data gets reused and which part gets cached. I'll touch on part of that in just a second, and we'll see if it's sufficient or not. So once you have a working data set that you want to train, this is just kind of an overview, abstract view, I guess, of what's happening. You'll have a bunch of readers that are needing to read from a pool of files. There's a bunch of work that happens within the CPU level. Files getting read into prefetch buffers, things get shuffled up, your CPUs will go through and decode and resize and distort. These will get thrown into a larger batch buffer. Those batch buffers will be sent off to GPUs to do their work. This might look a little different if you do know AI/ML workflows because we are using different flows. There's something called the Horvath model that we were looking at, I think, to make this happen. But largely, none of it matters because I don't care about any of that. So from the purposes of a storage benchmark for AI/ML, I don't care what's happening inside the GPUs and I don't care what's happening inside the CPUs. The only thing I care about are the operations that are going to end up affecting storage. So I care about these things like what is the reader doing to affect storage. So how do we find that out? Well, I guess before we find it out, when you abstract it at that level, what we saw by the systems that we were tracing is really there's only really 4 main operations that happen, and we can abstract them up into the big blue ones as 2 things. This is image processing, so we have lots and lots of small files. And the systems, the real systems we were looking at, we ran on all of them a pre-processing stage that takes the small files and creates much larger files. TensorFlow website points this out and says that reading large numbers of small files significantly impacts I/O performance. One approach is to get maximum I/O throughput is to pre-process image data into larger around 100 megabyte TF record files. We actually use 140 meg TF record files. But everything we did was doing that. So there's a phase of reading in small image files and writing out the larger TF record files. Those are the ones that are used for training and that are used for validating. So the training and validating phases will read in the real big TF record files, and then they do all that magic that was on the previous slide in the CPU, GPU, which I don't care about. Every once in a while, there's a checkpointing process. And so that's what we saw, and that's what we're reproducing, is the process of reading in the small image files, writing out the bigger TF record files, reading in the TF record files, and this occasional checkpointing. That's an excellent question, and it depends on the actual the data set, because each one of the data sets has a little bit of a difference. For what we modeled, I've got a chart, and I'll show you in a little bit. So how did we get our traces? So how did we know what was going on? For EDA and software build and VDI and all the other workloads, the way we normally do that is it's really simple. We take a Wireshark trace at storage to see what are the operations coming into storage. The goal, and this is a point of high debate within, I guess, the storage community and people who care about SFS. What is it supposed to be generating? Our goal is for it to be an application level benchmark. And the problem with doing it there, which we're still doing for some other workloads, like we'll talk about in genomics, but the problem with doing it there is I only get the things that make it to the wire. And what I really want are all of the I/O operations that are happening at the application level. So what we did this time is we ran strace on the server itself. And we then filtered out with the strace all of the I/O operations. So I think we actually took up an strace of everything. I don't think we ran like an FD and an FS type, or FS type, I think that's what it is, filter. I think we did everything, and then we parsed for the ones that we wanted. So that's what we did. When you do that, you get to see some really interesting things. So I'm just going to deep dive on one part of the strace. So I don't know if you've seen an strace before. They're really messy and they're really ugly. It's one line per system call. And so it will show you what the system call was. You can have it show you how long the system call took. You'll get any error messages from it. So I'm calling each one of those lines a sample. And so we parse through, this is an example of just the system trace information for part of the training process. But it gives you just an example of what we look through to make our workload. So what we see here, this has been filtered for the P reads that were being sent to one file, which also happens to be the trace of one proc, because there's a mapping between one proc was reading one file. But it's the P reads for one file. On the y-axis is the time. So where did that sample take place in time? And then the x-axis is the sample number. So you could have one P read, and the next P read to that file didn't happen for another 50 samples, which is why this is down here. But it could be really, really, really close in time because they could have been super fast. Or vice versa. They could have been one sample right next to the next one, but it could have been a long time between the samples. So when you see it like this, what you see is the P reads to one file. There's around 8 P reads to one file. Kind of ignore that guy because he's a little bit of an outlier. And then a big pause, and then a bunch more P reads, and then a pause, and then a bunch more P reads, and then a pause, and a bunch more P reads, and a pause. When you get the S trace, you can see what's happening is the process was doing a bunch of bursty 256K reads, and then it takes a mutex and just goes to sleep for a while, wakes back up, does a bunch more reads, takes a mutex. And we would never get to see that kind of behavior with an NFS trace. So we parsed the gigs of that kind of stuff. We ended up looking at, like, this is the p-read at time. It's the same kind of graph, except this is for all of the procs during this time period. And you can see that all the procs are doing something very similar. You'd have to zoom in a bit, but they're all doing something very similar. So the procs are, in this phase, we're doing p-reads of single files. If we, just for us to help make sense of it, we turn that into pictures like this. So you have readers that are doing bursty 256K p-reads. Full disclosure, we chose to model that within SFS using 2 meg reads because I don't have an ability right now in the benchmark to do sets of IOs. So the way that SFS works today, there's a histogram of IO operations and a histogram of IO sizes. And so there's a lot of histograms, but it's all histogram based. So you pick an IO operation and then you do it. And then you pick another one, it's all statistical based. I don't have a way right now of saying do 8 of that thing and then do something else. So full disclosure, and this is one of the reasons we're sharing this, is if you think this is a major issue, we want feedback on things like this of whether it's okay. We modeled that by 2 meg reads. Those are going to the training files. At an NFS layer, it didn't matter whether it's 256K reads or 2 megs, because if you use an R size of 64K, all you see are 64K reads, because they get transformed by your R size, W size. So the only way that's really going to make a difference is if you have bigger, like R sizes, which a lot of you may now. Used to be the default was 64K all the time, but so, and then what we saw is that procs are reading through a whole file before switching to another. So again, that's just one little picture of the kind of analysis that we did. And we took that analysis in its whole and then created this workload. So this is now an explanation of the SFS workload that is the current proposed AI/ML workload, which we're still calling AI/ML because image recognition is a really long name. We probably will have to change it, though, because we may want, what I'd really like is a series of AI/ML workloads that are applicable to you and like mean something to you. So here's what it does. Within SFS, the way that we do I/O is we create a load. There's a single business unit. So we're trying to represent one meaningful unit of business to you. So in a software build perspective, when you run the software build workload, we're trying to represent one software build. That's our load factor. And every time you scale the benchmark, you add an additional software build or more than one software build, which gives you a whole new set of procs doing work at a fixed I/O rate and a new data set. That's the standard way that we scale, and that's how we're scaling here, except we call it an AI job. Each AI job is trying to represent 1/10 of one GPU's worth of work. So if we actually scaled this to what we traced, most of you could never run it because it was a really, really big system with a bunch of GPUs running against a pretty hefty filer on the background. And if we just made that our standard load point, nobody could run it. You couldn't scale up to like 10 load points. And the goal was to make something that the average, like a smaller vendor or just even somebody with, who may never have a system that had more than one GPU, could run at least 10 load points. So we scaled everything back to represent 1/10 of a load point and created 4 sub-workloads. So the sub-workloads run concurrently and independently. So right now the benchmark doesn't have a way of doing a message passing between sub-workloads. So there's 4 concurrent independent workloads. One of them is the SF workload, stands for small files. It mimics reading in small files. One is the TF, which writes out the TF record files. One reads in the TF record files, and then the other one does occasional checkpointing. One of the goals of the SFS benchmark, and the reason a lot of people use it for regression testing and just quality use, is because it has some pretty high bars for success. For a run to be considered, a single load point to run successfully, all of the procs have to run, at least for this one, have to run at least 75% of their desired operate. So I'll show you on the next slide. SF has a required operate for reading in the small image files. So everybody has to run within 75% of their target rate. The aggregate rate has to be within 95% of its rate, of its goal. And then all of the workloads, all the threads within one of these workloads has to run with, there's no more than 5% variance off the mean. Yes, sir.
So the initial pool of data, in the set of data that you start with, is a whole set of files that, small files that can then be accessed to create the TF record file.
Yes.
Do you do any kind of locking to make sure that they don't get reused or stepped on?
So the,
Each one of them is unique.
right, there are some design decisions that we've made within the benchmark implementation to try to make sure that runs are extremely consistent run to run, and that you can run for an arbitrary amount of time without failure. One of those is that every run pre-creates the data set. So there is a data set creation phase, and then there's usually a warm-up phase and a measurement phase. We create all of the files required for every phase during the data set creation phase. They sit on disk, and then during the measurement phase and the warm-up phase, we just reuse the files that were made. So the file creation is a multi-threaded process that runs, there's a way to bound it, but it normally runs unbounded. So didn't mean to go here, but one of the interesting things with the benchmark is that the data set creation phase can actually be the hardest phase for somebody to, we don't measure it and there's no success or fail criteria, but it runs unbounded, and it can actually hit storage harder than anything else because it's a whole bunch of really large 100% write IOs that just go as fast as they can.
Why wouldn't you measure it?
That's an excellent question. I want that information in there, and it should be there. So I think we may or may not report that information as part of official benchmark releases, but it should be available as part of the log files that you can get.
Going back to the original thing I was asking about those, to reflect more accurately the nature of the environment that you're trying to emulate, shouldn't the data in all those TF record files be unique? So how do you make sure that the small
Right.
image files don't get reused?
Right. Okay. So the
You need some kind of locking or exclusion selection mechanism?
So the question for the recording is, how do we ensure within the small image files or even the TF record files, how and when files get used, reused? Is there any sort of locking to better reflect real-world applicability? I think there's a lot of stuff we could do that would make stuff even better. Right now, we just create a large data set, and we're the TF record, or reading in the small files, is a random read out of all the files that are in that pool. In order to run this for an arbitrary amount of time, you would have to know in advance how long you were going to run and create a much, much bigger data set, potentially, or you're always going to have to go back and run. So I think right now it's set to be uniform distribution, and so it just uniformly makes random selections through the data set. A lot of what you're asking is tied into how long are you going to run, can you support an arbitrary length of running? In order to do that, we don't bother locking them, we just read files. And so they can get reused, and the TF record files can get reused, and you'll see that in a second.
But
It's
also,
an
all the
excellent
sub workloads are gonna be separated in terms of their data set that they use, so they can't step on each other.
Oh, that's
and
true.
because the file sizes will be different, and then each thread, I believe, for all these workloads is also going to have its own area to play in. So we're making sure that we're not like artificially re-hitting files more than we intend, based on the data set definition or workload definition. Sorry.
Okay, a couple more things. How am I running on time?
35.
Okay. So just a bit more details. So there's like the small file workload. There are 4, so for every AI job, which again is our basic unit of measurement, there are 4 of those running. They run at 100 ops per second, which implies that they have to run with a maximum response time of 10 milliseconds. They run against 1 meg file, so that was the answer to your earlier question. There's 200 files per directory and 3 directories, and again, every time you do an extra AI job, you get a whole other one of these. because they scale up each time. They're aimed mostly at doing reads, but what we found is that because there's a whole bunch of files and you have to find the files, the traces actually show a lot of stats. So you have to find the file in order to read the file, so it's a mix of stats and reads, and they tend to be larger reads. The TF record writer, there are 2 of those. They run at 2 ops per second. It's not very fast. 140 megabyte files that they're outputting, and they're 100% writes. The traces show a whole variety of write sizes. I would have expected it to just be big dumping, but it's not. It's a whole variety of I/O sizes. The training file is then reading in the 140 meg files. It's a different file set, actually, but it's the same file type. 95% large reads, and then that check pointer I mentioned, he's just out there. The S-traces just show this lone thread out there occasionally writing either little bitty IOs, like less than 512 bytes, or 2 meg IOs. So we've got a little occasional writer who's out there. So that gives you, per load point, about a 10 meg. I think that's, oh, sorry, I was reading it wrong. Right, so we've got about a 10 meg average file size, average data set size of 88 gig, 17 client processes, which again, that scales every time. An aggregate metadata, read-write metadata operate at 435 ops per second, and 91 meg per second. So your minimum, the minimum required of a storage array is to be able to deliver that, and then that can scale up. So what I'm going to do is I'm going to show you some real-world numbers, some real-world results from people who've been running this.
And if I can pile onto that, that means the minimum publishable is actually 10 times that. So if that number seems low, that's because the minimum publishable is actually 10 load points.
So this is at least 10 load points. So the normal way of showing SFS results is you plot the latency on the y-axis and you plot your load on the x-axis. So I'm charting this as achieved operations per second. I could chart it as AI jobs, or I could chart it as SFS 2020 reported megabytes per second, because they're all the same thing. Your ops scale with your jobs, and the megabytes scale with the jobs, because it's just a unit that you're reproducing over and over again. So you get a chart that would look something like this. Again, these are, I'm purposely obscuring which vendor out of the committee chose to run it and what system they ran it on, but they're real numbers. Yes, sir.
Some of the GPU clusters, like the NVIDIA DGX1, have a very large local flash caches.
Right.
In the case of the DGX1 is 8 terabytes. And you just said that your data set size was 88 gigabytes.
Per load point.
Okay. So would you so you could actually, most of these open source data sets would easily fit in terabytes.
Right.
So you could run it all locally, and you wouldn't need any file performance. So would you just bypass the flash? Is that kind of what you're doing? Not storing it?
So one of the interesting things about the current implementation of the benchmark is that it does everything at a POSIX layer. So if your OS has the ability to cache data and it chooses to cache it in an NVRAM of some sort or an NVDIMM or something, then you'll get cached. All we dictate is at an application layer, do these amounts of reads or writes, and the OS has the ability to cache whatever it wants, which I'll show in a moment. Does that answer your question?
Kind of, but I mean, for like a practical usage of, if you have one of these DGXs sitting around to do your training, you know, the normal practice would be to stage all your data there and then run it off of that. Right?
Right. Okay. So
that's just like a practical thing what people would do.
Okay. For the audio recording, the question was that there's often a very large cache available on some of the boxes, like a NVIDIA DGX box, and that some people would store their entire data set there and try to avoid going to storage. How do we deal with that in the benchmark layer? I think you could just dictate that your store, when you run this, as opposed to being on an NFS store, was on that local store, and so you could measure it that way, because you would still have a data set that you were storing and accessing. But that's a good question. From a time perspective, I'm going to keep running through this, but we should one of the goals of this is to create something that people are willing to use. Like, I'm investing in it because I do a lot of AI/ML work, And I want something that I can run without having to have a big DGX box to have to hit my filers with. So I need something that's relevant, and so that's a good question. So we get a curve that looks like this. Because we're using sub-workloads, I can actually look at the performance of all the sub-workloads, which is really neat. So what I've done here is I've scaled all the sub-workloads so they fit on the same x-axis. Because remember, like the checkpointer, he's only doing 1 op per second. So clearly, he's not going to hit the same maximum ops per second that everybody else would. So I've scaled it. I've normalized everybody so you can see. But it's kind of cool. Like you can see that the SF guy, the small file reader, he's got the best response time over everybody, even though he's doing a lot of reads. That checkpointer's got the worst response time of everybody, even though he's not doing anything. So it's cool how you can see how a single storage array, for example, can deal with a mix of IOs all happening concurrently. You can also see things like this. So over here on the right-hand side, everybody's scaled, so they should all be hitting the same ops per second at every point. I can see that this guy, the small file guy, ended early. So he's the guy who failed my success criteria, and the benchmark died at that point because that guy, his response time was too high. And so I can see that the small file reader in this case was the guy who bombed out. And you can also see that it's a relatively well-balanced workload because the other guys, the training workload and the gray one, the TF file creator, they almost certainly would have bombed out on the next workload, on the next load point, because their latency is skyrocketing at that point. It is an application level benchmark, so I'm going to show this because it's worth discussion, although we got to let Nick talk about genomics, I think, before we take more questions. But all application level benchmarking is subject to what I'm showing you here. You can say that this is great, or you can say that it's terrible, but it's what happens. So I'm showing this, but realize that this is applicable to VDBench or Iometer or IOZone, anybody who's working through the OS and file system layer. So what I've done is this is exactly the same run as this, but what I'm charting here is the operation mix as it was delivered to storage. So if I had just done an NFS trace, for example, these are the operation mixes I would have seen, and it would have depended on what load point I took it at. Because what we see is that the clients are actively caching data, and what they cache changes as the load on the client increases. So as that goes on, we move from the client, delivering a lot of get adders to storage, to eventually delivering a lot of reads to storage, because it can't effectively cache the metadata and
client-side settings like ACDO cache and all this stuff?
Nope. So the question was, do we prescribe client-side settings? We have a best practice document that recommends what to do. This is one of those things about a large solution-oriented testing. A vendor, just for full disclosure, a vendor could get this behavior by quadrupling the number of clients for their publications. And then part of the goal is actually, this is a really good reason that for SPEC to exist. Because as a committee, we ask some really hard questions during publication review, like, did you actually do any I/O to the storage array that you're claiming to do a marketing publication for? And they're not required to answer, but you can generally tell by the way that somebody chooses to answer that question. And it's good to push people to, like, why are you doing what you're doing? Is it valid? Is it meaningful? And so forth.
And we do prescribe what needs to be disclosed in a full disclosure report for any published run.
So because of that, this is the actual megabytes per second delivered to storage. If everything that the application was doing made it through exactly as the application asked, you would see a chart that looks like this. But in reality, we saw this one because as we transform to more and more reads, you get like more and more megabytes per second because reads are doing more megabytes per second than metadata is. All right, so why am I showing you all this? And so how do we wrap up AIML? The current proposed workload for AIML image recognition is focusing on the dataset phase and the training phase. I said validation too, because I think validation looks very, very similar. But the dataset and training phases of image recognition. There's 4 concurrent independent sub-workloads. Like any application level workload, it can be affected by client-side OS behavior. And we're showing it because we want input. We want hard questions as a committee. We want those. We want to create something that you're willing and you want to use. So, and what we really want, just to be honest, we want more people in the committee. So I would love for more of your companies to be, active participants in the benchmark design.
All right, let's move over to a brief look at our proposed genomics workload. And I just want to give a shout out to Dell EMC, who is the workload sponsor, and they've done a lot of the testing, tracing, and education of us on what this looks like in the real world and in their well-equipped lab for testing this. So really, when you talk about genomics, what we're talking about is next generation sequencing, or I believe high throughput sequencing, which is the predominant technology right now. And we want to focus on what are the storage needs of next generation sequencing environments that are sequencing these genomes through the whole analysis workflow. But only like with AI image processing, we just want to focus on what are the storage needs, what are the demands of storage to support this workload. Because, genome sequencing is a very compute-driven thing. As compute has gotten cheaper and as the sequencers have gotten better, we're doing more and more of it. And it's amazing if you look at the research out there for just how much data is being used and will be used in the future just from next generation sequencing workloads. I mean, it eclipses all the cat pictures that are getting uploaded to Facebook by like orders of magnitude. So that's why we really want to focus on what are the demands to storage arrays to support these workloads, because more and more of it is happening. It's like $1,000 now to sequence a genome when it used to be tens of millions or more of dollars. The nice thing is, because it is an HPC type workload, shared storage is very popular. It's the predominant storage type because you have a whole compute grid that has to access the same storage. So you're typically going to have some sort of shared network storage. And that is really in the wheelhouse of the SPEC Storage benchmark and or committee and the benchmarks we produce. So what does a gene sequencing workflow really look like? There's a primary analysis phase, a secondary analysis phase. Really, the sequencing is part of the primary analysis phase in the way most people think about it, and then there can be further analysis phases afterwards. But let's separate sequencing for the sake of looking at this. What is sequencing? Well, that's where you have the actual device that takes the physical sample and converts that to digital data. So that would typically produce a BCL file, I believe, through image analysis. And then after that, you're going to have, and it depends on the sequencer you're using, but you're going to have a series of steps there that's going to take the output from the sequencer and assemble all of that into a larger FASTQ file, or a series of FASTQ files. And once you have the FASTQ files, you're going to do a secondary phase of analysis, at least, that's more filtering the data for quality, doing alignment and assembly of the actual genome itself. In just sort of one example at these different steps in the pipeline, for example, the sequencing workload would generate in this one scenario, about 6 terabytes of data in about 44 hours. Then that primary analysis phase, after sequencing, that's more than 6 terabytes of data in about 24 hours. And then secondary analysis, it would vary, but it could be about 12 terabytes of data in about 48 hours. But that's really going to depend on the data governance policies at the specific site. What I've been told is that the scientists tend to hoard as much of the intermediate results as possible. So if they have to rerun a step, they don't have to take as long to do it. But there's also a limited amount of shared storage. So it's a balance between what people want and what people can have in terms of data storage. So what are the challenges for making a genomics workload? There's a lot of variation in the workflows. I mean, there's different sequencers to start with, but people are using different applications. There's a huge open source ecosystem of tools that are used, and people really are trying to get different results at the end. They care about different things from the data. And one thing that may help in the future is FDA-approved diagnostic tools, because those will force a very specific workflow, because it's an approved sequence of steps that's like insurance billable. But basically for genomics, we're trying to take a similar approach to what we did for the EDA workload in SFS 2014. And that's to look at the aggregate workload that's presented to the storage, because in these environments, like I said, it's a large compute environment. And in that case, you're going to have a lot of jobs running at once, because one single job is not going to be allocated typically the entire compute grid, because it probably can't make use of it, or it's certainly not fair for it to make use of the whole thing. So the jobs aren't synchronized. There's not just one phase of a genomics pipeline happening at once. It's all happening at the same time. So it makes sense from that perspective to make an aggregate workload, because all the different phases will be going on at once. That said, we do actually want to understand what each of the phases looks like. Now, it's going to be different at every shop, but we're going to take the Dell EMC lab, and we're going to go through what their expert says, is a typical 9-phase analysis pipeline, and we're going to do an S-trace and a network trace, like Ken was pointing out, for each of those different phases, so we can understand each phase. And we're going to boil that down to sort of the fundamental characteristics that we care about, and produce from that a minimal set of unique workloads. So maybe they're all unique, we need 9. Maybe they're all the same, and we need 1. Well, for AI image processing, we wind up with 4. So we're going to see what we wind up with for genomics. We're not sure yet, but that's sort of where we are. Once we've done that, we want to make the workload in our benchmark and then validate that against real-world environments. So where are we right now? We've collected the traces for the 9-phase analysis pipeline. Like I said, we've collected traces from a single real-world environment. So if you have access to a real-world environment that we could get traces from you or work with you to get traces, we would love that. And we've completed an initial analysis of the op mix from both of those different environments. So we're really seeking more real-world environments at this point to validate against. And we're doing further tracing and more analysis of the traces that we do have, because it takes a while to pour through all those traces. So here's, from the 2 environments, the observed op mix that we have. Excuse me. And they're a little bit different. I mean, they're similar, but they're also a little bit different. It's important to note in the test lab run, which is the orange or the second bar for each of these ops up here. In that case, the data prep phase was skipped. In the real world environment, the data prep phase was ongoing, randomly, like I said, because all the phases were running. Also, from the test lab run, that's where we ran the phases separately, and then we put it together. And that was our first attempt at putting it together into a workload that should match the real world. So you can see we're close on some ops, we're off on the others. So we're deep diving now to understand where were the differences, why were those differences there, and how can we adjust things so our workload more matches that real world. And that's why we want more examples to compare against and more traces to compare against to try to figure out, okay, what do we need to do to make this reflective? Because certainly comparing to one real world, lab that's not how the entire world looks. Hopefully the entire world does look somewhat similar though. But we do want to validate that and be very confident in that. So finally, our intention with a genomics workload, and we don't know if we're going to call it genomics or next generation sequencing. Genomics, again, like AI ML, is quite vague. We may want to get more detailed later on, especially if there's like an FDA approved workflow. We'd rather capture that if there's a fixed workflow. So the name is up for grabs, but we intend to represent that entire pipeline from sequencing to final analysis. We're seeking more real world environments to validate against. And you can help us shape this, by joining us on the committee. And I sort of want to point out another thing that Ken said. Just like AI/ML for genomics, I mean, it's great that all the open source tools are out there, but you do have to have the data sets. You do have to have that compute environment if you want to replicate it. So just like with AI image processing, what we want to do is we want to provide an easy way for storage vendors or anyone else to assess how well does this storage solution work for supporting a genomics environment without having gene sequencers and an entire HPC compute grid at their disposal, because it's more economical, it allows faster iteration, and it allows storage vendors to improve their products to suit that application at a much higher velocity. So that's sort of our end goal. I think we're pretty close on time. Yeah, we're at about exactly time. So we will take
Nick,
questions in the hallway track, I think. But
So
Ken, you wanna wrap up?
Nick and I were both mentioning it'd be nice to have people participating in order to like analyze data and make sense of data. One thing, so like in AIML, if you have an ability to get a trace of a real world in like real life image recognition, image processing system, and that's what the storage is handling, we would love like data off of your storage array. We'd love Wireshark traces, or if you have the ability to get a trace with PyTorch or Caffe or something else, just to be able to compare those to the TensorFlow network and see whether or not we could say it's a TensorFlow only benchmark, or we could say, hey, it's an AIML image recognition. But the same way with genomics. Even if you're not able, as a company, to participate at a committee level, if you've got access to network traces or to S traces, if you can get us data, the whole point, what we do only matters if it matters to you. I use the tool every day. I mean, and I know there's other companies here that use SFS every day for engineering purposes or customer escalations and stuff like that. We were using it last week to help reproduce a customer case because it's so flexible in what you can do. But from a spec perspective, in terms of getting spec's name out and being able to publish and give in a vendor neutral way, what we do only matters if the real workloads matter to you. So any input you can give would be great.
Yeah, don't hesitate to email Ken or me. Our email addresses are on the first slide, so don't hesitate. We can connect you with the spec. We can connect you with anyone. And we can, if you're interested in just helping a little bit, we can invite you as a guest to participate in our official technical meetings. So don't if your company isn't on the list and you don't want to spend the money to join, but you want to help out, get in touch and we'll find a way to make it work.
All right, at this point, I think we'll turn the mic off, but if anybody's got questions, we can take them in the hall or take them. Oh, sweet. All right,
we do?
got 4 minutes for
Sorry.
questions. Anybody have questions?
I didn't you had questions.
Okay. Yes, sir.
What are the file sizes and distributions for the genomics?
We're still trying to work that out. I did have my colleague at Dell EMC email me that last night, but I didn't have a chance to fully digest and understand it, so I didn't want to share it with you. We do have that. We're coming to consensus on that probably by the end of October, I think. We're hoping to have a first pass at that. So if you, again, I don't know if your company's a member of the committee. If you are, then we can share that with you. Otherwise, maybe we can, get you in as a guest. And
the question for the recording: what are the file sizes and file distributions for the genomics?
yeah.
There is a good breakdown that describes it at the Broad Institute website that shows exactly what the sizes of files to get, sequencing files to be bought.
I'm sorry. So you said that there's a resource out there that has a good breakdown for this. What was the resource?
It's on the Broad Institute website. I can send you the
Okay.
Yeah.
So again, for the recording, that the Broad Institute apparently has a research paper that shows the file sizes.
It is nice because you can get a lot of the data out there in sample data sets.
Other questions? So Jim, I'm just curious. When you all see stuff like this, because I have been to some presentations, and I've been to some presentations this week where I thought, well, that was useless. I mean, it was an interesting talk, but I was never going to use it. Is this valuable at all? I mean, is what we're doing useful? Is it going down the right direction? I see some nods. Okay.
What version of SPEC, like the actual software to run these workloads?
So the question was, what version of SPEC do we need? In theory, you could run the basic workload definitions for both of these with SFS 2014. But in the end, you'll need SFS 2020 for a variety of reasons. There is a scaling limitation right now to SFS 2014 based on the number of TCP ports that you can open. And the 2020 revision is completely revising the way that client nodes communicate to each other. There's a new 3-tier architecture that will allow it to scale really, really far. And we expect that because there's so many threads with the AIML workload, 17 per load point, that you'll run out of TCP ports before you can scale as far as you'll probably want to.
What was the story? Who's maintaining that software stuff?
SFS?
All on GitHub, or-
No, so the software is
SPEC
under
Storage.
SPEC Storage. The SPEC organization and then the storage subcommittee handles all of that.
Yeah.
Okay. Any other questions?
Yeah, and just to add a little bit to that, I mean, the code is owned by SPEC, the nonprofit, and it is source available. So if you buy a copy of the benchmark, you do get the full source with it. And then if you're a sustaining member, you do get access to the source tree as well. Just to be more specific.
Yeah, that's been our biggest challenge with SPEC is through different versions, compiling it to different clients, and we get random TCP errors, and, sockets closed, and stuff like that. Trying to debug that has been a barrier for broader adoption of SPEC.
So there was a comment that apparently, and is that for SPEC SFS? Or,
SPEC SFS.
okay, that there's been some issues in the past with trying to compile and use.
2008?
Probably.
Yeah. We retired 2008 for a reason. It reached end of life with newer operating systems is kind of what happened there. But yeah.
I'm excited to take a look at it.
Yeah. Yep.
But you have to be a member of the SPEC organization to get access to this country. You guys get pull requests or any of that kind of stuff. Like, where is it truly an open source product or?
So the question is tied into how do you get access to source and how open source is it? So Nick just said this, but I'll say it and he can correct me if I get it wrong. If you buy a copy of the SPEC SFS storage benchmark, it will come with source, like you buy it on CD or it's a single downloadable, and you'll get source. If you are a member of SPEC and you are a sustaining member of SPEC, then you have access to the Git repository and you can do pulls. You can't contribute unless your code has been reviewed by the SPEC Storage subcommittee, because we'll have to, but you can do pulls.
Okay.
All right.
Thank you,
all.
everyone. Appreciate it.